Problem 2114 is a helicopter problem, and they ask you to approximate the helicopter blade as a parallelepiped rotating about an axis like this. So they give you the length from tip to tip is 15 feet. Go ahead and leave that in feet. They give you the width right here is 5 inches. Convert that over to feet, and the thickness is 3/4 of an inch. Convert that to feet as well. They give you the density of the material that they're using there, and unfortunately they give it to you in CGS units, so convert that over to pound masses per feet squared. They also tell you the initial rotation frequency of the helicopter blade, and then what it rotates up to, the new rotation frequency. You'll need to multiply this by some conversion factors. This R is revolutions, and 1 revolution is equal to 2 pi radians. So 1 rev is 2 pi radians, 1 minute is 60 seconds. Convert all of that over so that you get something that is in radians per second, and this is the initial and final angular velocity. Convert the time over which the speed goes from this to this. That's 3 minutes. Convert that over to seconds, and you can solve for alpha. So that gives you the first 3 blanks on there, omega initial, omega final, and alpha. Express those in radians per second and radians per second squared for alpha. There's 2 blanks missing for this problem. If you look at the statement of the problem, it asks for us to find the torque, which we're going to use capital T like they do in the textbook. In this particular section, also called the moment, and you want to express that in foot-pounds or pound forces times a foot, and they also want the mass per unit time for the flow rate from the second propeller out on the tail in pound masses per second. The way that you begin to find the torque, capital T, is you need to find the moment of inertia, I. If you look at the table in the textbook for a parallelepiped, you'll see that it's 1/12 m a squared plus c squared. We'll have to multiply this by 2 because there's 2 long blades, so it's 15 feet from here to there, but then there's 2 overlapping blades like this. So that's why you'll have to multiply this by 2, because you have 2 blades on your helicopter. So you'll have to express that in pound masses times feet squared once you put everything in. One thing I left off here is if you'll find the mass of one of the blades, just take the density times the volume, or take the density, multiply it by A, B, and C. That's the mass that goes right here. In linear motion, Newton's second law says that the summation of the forces is equal to ma. In rotational motion, it's the summation of the torques is equal to I alpha. So when they ask you to find the torque, what you do is you find the moment of inertia I and multiply it by alpha. Alpha is what we had found previously in radians per second square. I is what you find on the previous row. And I think the units will come out to be pound masses times feet squared, and then you'll get the radians per second square, so it'll just be per second square. Now what you'll have to do is use a conversion factor, and that conversion factor you'll probably remember is 1 pound force is equal to 32.2 pound masses feet per second square. Use that conversion factor to get torque in the units that they request, which is a foot-pound. And to find the mass flow rate, you'll have to read the statement of the problem to understand what I'm doing right here. But just quickly, I have the impulse momentum equation. Initial momentum plus impulse equals final momentum. I solve for the mass flow rate out of that, and I get that it's the force from that second propeller divided by the difference between the final and the initial velocity. Also, to find the force, you can say that it's the torque that you get from that previous calculation divided by the 20-foot difference, or 20-foot distance, between one propeller axis and the other. Using all of that and the previous results, you'll have to look up what V final and V initial is in the problem. I don't have them stated on this page, but you can do that and then get the answer in pound masses per second.